Okay, here in Lesson 10b, we're going to talk about an unusual thing we can do with a normal curve. It only occurs in more advanced math classes like Honors Finite Math or AP Statistics, so we made this a separate video. Under some circumstances, we can do a very unexpected thing. We can use a continuous probability model, the normal model, to approximate a specific discrete probability distribution, the binomial model distribution. Okay, so remember when we looked at the distribution for a discrete binomial model, recall that we said that the shape of the distribution depends upon the probability of success p. If we had a probability that was 50% right in the middle, then even with a low sample size, the probability would be symmetrical and centered at 50% of the outcome values. But if we had a low probability of success, like 0.2, the probability would be skewed right. And if we had a high probability, like 0.7 of success, then the most commonly occurring value would be 70% of the outcomes, and the distribution would be skewed left. Okay, so the binomial distribution also turns out to be dependent upon another factor. In other words, the shape of the distribution depends not only on the p-value, but it does depend on the sample size and the total number of outcomes. Because as the number of outcomes goes up, a strange and unexpected thing happens. Even if the probability of success is not close to 50% and the distribution starts out skewed, the distribution becomes more and more symmetrical as the sample size increases. And at some point, it starts to resemble a normal shape. This is a totally counterintuitive result, and yet it's really true. And you can use our tactics that we talked about of populating a calculator's list 1 with possible values and then using the binomial PDF function to see the distribution with a scatter plot. If you go back and look at the discrete probability distributions lesson video, that will show you a procedure for doing that. But here's some examples worked out. If we had a sample size of 5, n is 5, and the probability of success was 0.2, then NP, which is the number of successes, would be only 1, and we would have a very highly skewed right distribution like this. If the sample size was increased to 10, then it would still be highly skewed. If the sample size was increased to 20, it starts to become more symmetrical. Not perfectly symmetrical, it's still skewed right, but only slightly. By the time we get up to n is 50 or n is 100, then these curves look actually very close to perfectly symmetrical normal curves. Counterintuitive, and yet it's true. In fact, above a certain limit, we can use a normal approximation. In other words, we can approximate this discrete distribution of individual values with a continuous normal distribution that has a specific mean and standard deviation. And the cutoff for when we can do that is when the expected number of successes, which is what in the Poisson model we talked about was lambda, is n times p, and also the expected number of failures, n times q. If they're both at least 10, then that means we can use a normal approximation for the binomial distribution. We can use a continuous model to approximate a discrete model. Okay. Now, if we decide that we're in that region where we have a high enough sample size that we can do this, then we have to specify, well, what is the mean and what is the standard deviation of the normal curve that we're going to use? And it turns out that it's given by the mean and standard deviation formulas for the binomial distribution itself. The mean of the normal distribution will be centered at n times p, the number of successes, and the standard deviation will be the square root of n times p times q. Okay, so let's take an example. Let's say that we have a sample of 50 bats that are collected from a cave known to harbor the Ebola virus. If the probability of a bat having Ebola in this cave is 60%, then we maybe want to find what is the probability that more than 32 bats in this sample of 50 will have Ebola. Now, we could solve this using our standard binomial model. We could define a random variable x that represents the number of bats out of 50 that have Ebola, and the possible outcomes would be anything from 0 all the way up to all 50 bats could have Ebola. And if we want to find the probability that more than 32 bats have that would be on this side, so it would be all the outcomes from 33 to 50. And we know that we could find an individual probability with a binomial PDF. we can use binomial CDF to find a cumulative value up to and including that. But for right side problems like this, we'd want to take 1 minus the binomial CDF representing the opposite side. So it would be out of 50 bats, 60% chance of having Ebola. 32 would be the upper value from 0 to 32, and if I subtract that from 1, I get the right-hand side probability here, which would be 23.69%. 0.2369 is the probability, and that's the exact probability in this case when we solve this with a binomial model. But what we're saying is, if the sample size is large enough, and that would mean the number of successes and number of failures would have to be at least 10, then that means we would be able to approximate this with a normal distribution. So n times p is the number of successes. 50 times 60% is 30 bats, right? And that means the number of bats without Ebola would be the other 20 bats. Both 20 and 30 are above the magic number of 10, and that means that this is going to be symmetrical enough to approximate with a normal distribution, and the mean of that distribution would be the n times p, 30 bats, and the standard deviation of that would be the square root of NPQ, so the square root of 50 times 0.6 times 0.4, which is 3.4641 bats. And that means that I could sketch this distribution, mean of 30, standard deviation 3.4641, which means plus 1 standard deviation is about 33.46, and minus 1 standard deviation is 26.54. And so if we're trying to find the probability that more than 32 bats have Ebola, then I could put a boundary value here at 32, which I estimate to be approximately here, and then we'd be shading the upper part of that curve, and that means we could use a normal probability function from 32 up to something representing infinity with a mean of 30 and a standard deviation of 3.4641 gives me 0.2819, which was fairly similar. That was fairly similar to the value that we got with binomial was 0.2369. So we had 0.2819 for the normal approximation and the fully correct value 0.2369. Okay, so why would we use a normal approximation when we can just do the problem directly with the binomial model? Well, you know, the binomial model is really the correct one. So in this case, it's just easy enough to do that with the binomial model. There's no real advantage to using the normal approximation. But there are some historical reasons why the normal model was used prior to having good technology that we have now. The manual calculations for binomial model turn out to be more difficult in cases where n is very large, and the normal model calculations were easier because those were always done by looking up z-scores in a table. So it turned out that it was easier, just physically easier, to do the normal calculation for large values of n. And as a result, this concept appears frequently on the multiple choice portions of the AP statistics exam. For some reason they still put that on, even though this is kind of a historical oddity. But there is still a good modern reason for using the normal approximation. We didn't see it in the Ebola problem there, but consider this binomial setting problem. Let's say students take a 50-question true-false test. Even if a student doesn't truly know the answer to a question, they could guess and still get it correct. In fact, they could be guessing on all the test questions. So how many questions would a student have to get correct before you would conclude that they're not just guessing? So let's say that there should be only a 5% chance of them getting this many questions correct if they were guessing. And we want to figure out how many questions that would be. Okay, so if the student is completely guessing on this test, then that means the probability that they get an individual question right is 50%. There's only two answers, true or false. This probability is going to be the same for all the questions if the student is truly guessing, and it's going to be independent from question to question if the student knows nothing at all about the subject matter. So they get each question either right or wrong. That's a yes or no case with a constant probability that's independent. That qualifies as a Bernoulli trial situation, and because we have 50 questions, that's a known number n, and that means this specifically is a binomial situation. So we could definitely do this with a binomial problem. Right? We could make a probability model and say that x, the random variable, represents k correct out of the 50 questions. Anywhere from 0 to 50 could be correct, and then we could find a probability. The problem is that we don't really have we're trying to figure out how many questions. In other words, where should we set this boundary value to figure out when the probability drops below 5%, right? So I guess what you could do is you could like pick a value, like make a guess, and just say, well, let's guess 29 questions. What if they got 29 questions correct? What would be the likelihood that would occur, right? So they could get up to 29 questions correct, and we could figure that out with a binomial CDF function by doing 50 questions. Probability of an individual question being right is 50% up to 29, and that would be 89.87. And we could keep doing that guess and check until we find a value that drops below 5%. So something where this calculation is 95% or above, right? That's not a very elegant way to do the problem, but it would work. We could just keep trying. We could try 29, we could try 30, we could try 31, 32, 33, and keep going until we found a value where this probability value here was higher than 95%, therefore meaning there's a 5% chance or less of them getting this many correct just by guessing. Again, not a very elegant way to solve the problem though. So is there a way where we could solve the problem more easily? And we could do that. If we were to use a normal approximation, then we could use the inverse norm function to find the boundary value. Let's explore this further to see what I mean here. The mean and standard deviation, in this case, we have 50 questions. There's a 50-50 chance of getting them right, so they should get half right and half wrong. So NP would be 25. And NQ would be the other 25, so that's above the 10 threshold. That means we can use a normal approximation for this binomial model. The mean would be 25, correct, and the standard deviation would be the square root of n, which is 50, times p, which is 0.5, times q, which is 0.5, which means the standard deviation would be 3.5355. And here's a sketch of the normal model for this binomial distribution. Okay, if we're interested in saying how many would you have to get right, where we would think there's only a 5% chance that would happen randomly, I could say, okay, there's some boundary value here which I don't know. I don't know this boundary value, but I want some value where the probability of being that or higher is 5% or less. So that means we're trying to find a boundary value where 5% is to the right of the curve. And that means that there would be 95% of area to the left of the curve. And we could use our inverse norm function where it will give us an x value, a boundary value, where 95% of the value is below this curve if the mean was 25 and the standard deviation was 3.5355. And that turns out to be 30.81. And that means that the student would have to get 31 of the questions out of 50 correct for us to be sure that the student wasn't in fact guessing, or at least to say that there's a less than 5% chance that this would happen due to lucky guessing. Now, if we had done guess and check using the normal CDF, or the binomial CDF function, sorry, for the binomial model, right, we might have had to try quite a few regions before we stumbled upon that 31 was the first value that had this left probability above 95%. So anyway, this illustrates a more modern reason why we might want to use a normal approximation whenever it would be advantageous to use an inverse norm function to find a boundary. Alright, so just to summarize this, as long as the number of successes, n times p, and the number of failures, n times q, are greater or equal to 10, then a binomial model can be approximated with a normal model, and we just use the binomial model mean and standard deviation formulas for that. And then all of our tools for normal models like normal CDF or inverse norm become available to us.